In 1928, a professor goes on vacation and returns to his lab to find something he later calls mold juice. And this, quote, juice has since saved thousands, if not millions, of lives. Then, 30,000 years ago, some DNA literally frozen in time held on to an Ice Age secret that scientists only recently discovered. And in the 1960s, researchers found an organism thriving in one of the harshest environments on Earth, where life was thought impossible. Gina, all these moments in history lead to...
Okay, David, I don't know what this topic is, but it sounds...
Okay.
germy.
Germy, yeah. One of these days, I am going to finish that last sentence of my intro. Every episode, you kind of cut me off.
Like germy, like...
Okay.
I've got these hand sanitizers on my desk. I'm kind of wanting to just start spraying them,
Okay, got it.
I feel like there's things crawling on me.
Yeah, I guess we'll discuss manners later, but back to your hand sanitizer. Mm-hmm. That actually might not be a bad instinct.
Oh man, Are we talking about bacteria today?
Bacteria. You wish. It's much worse than that. Oh yeah.
Worse? Mm-hmm. Worse than bacteria? 'Cause
definitely
bacteria
worse.
Pretty bad, David.
Today we are talking about antibiotic resistance.
This is Inflection Point.
Spanning a century of reporting from C&EN, this new podcast traces discoveries from our past
to how they shape our present
and will change our future.
I'm Gina Vitale.
And I'm David Anderson.
David, I don't know if you know this about me, but I am a bit of a germaphobe. On my desk right now, I have 2 hand sanitizers.
2 hand sanitizers? Okay, wow.
2.
All right, understood.
Because if one doesn't work, you need a backup.
You need a backup. Fair enough. Well, I don't know. I couldn't relate less. I'm actually pro-germ.
You're pro-germ. Well, gross. Because I am such a germ hater.
Okay.
I think I'm just going to take a step back. I think I am just going to let you do this episode on your own.
Okay. All by myself? The whole episode?
It's all you. You've got this.
Okay. Okay. That's not a problem at all. I can handle this.
Yeah. Take it away.
First thing I was going to ask you, which of course I don't need to because I know it anyway, is what is a germ?
Great place to start.
I can take a stab at it. A germ is like a little insect. It's about the size and shape of a sprinkle.
An insect?
Like the rainbow sprinkles that you put on ice cream. That's what a germ
okay.
is.
All right, David.
They crawl around.
We're coming back in here.
Okay. Oh my God. Thank God
David,
you're back.
That is 100% wrong.
Oh my God. I knew it was wrong. I panicked. I freaked, okay? You left me all by myself. I had no
really
idea.
Panicked.
I started talking about ice cream. I'm not even the ice cream guy. You're the ice cream guy.
You got to leave ice cream to me, man.
Oh
yeah,
God.
Okay. Look, I'm back now, so just, take a breather.
All right.
Relax. Deep breath in. Yeah. I certainly cannot leave if you're going to tell our listeners that germs are the size of a sprinkle.
I didn't know what to say.
That is not true.
I mean, my head was spinning. It was terrifying.
Yeah. So germs, which are also called microbes, are not visible to the naked eye.
Okay.
And they are definitely not insects.
Okay. Learn something new every day. What are they then?
Well, there are a few things that can count as microbes. For instance, viruses and fungi. A really common type of microbe that we'll probably be talking about a lot today is bacteria.
Okay, let me make sure I'm thinking of the right thing this time.
Sure.
I'm picturing a little cylindrical thing with little hairs sticking out all over the sides.
Yeah, I think you are picturing a bacteria, although they can be several different shapes. And something you didn't mention is that bacteria are single-celled organisms. That means their whole body is just one little cell.
Wow, okay, that's pretty cool. Or maybe not cool, I guess, if they're bad for us.
Yeah, well, a lot of them aren't. Some of them are helpful.
Okay, so being pro-germ doesn't sound so silly, now does it?
It still sounds pretty silly to me, to be honest. But some of them can make us really sick.
Okay, and how do they get to us exactly?
A lot of ways. So for instance, you could touch something with bacteria on it and then touch your mouth. Someone else might cough them out and you could breathe them in. You could eat them, you could drink them.
Ooh, okay, got it. They have many, many different ways of getting to us. So I suppose antibiotics are pretty important.
You might say that, yes.
By the way, do you know who discovered antibiotics?
Yeah, Alexander Fleming discovered penicillin. I mean, everybody knows that one.
Okay.
I'm sure that's not an inflection point, because...
For instance, if it were, I mean, for the sake of an upcoming inflection point, could you pretend like that fact is a little bit more esoteric?
Well, David, I mean, it's fairly common knowledge. I mean, like every grade schooler probably knows that, right?
What grade? You went to Genius Elementary or something. I don't know what grade school
I
teaches
did go to Genius
about.
Elementary. I was the valedictorian.
Figures. Okay. Well, did you know this? Fleming discovered this stuff on accident.
Yeah, he ate a moldy orange or something while he was on vacation, right?
No. I thought you would know this one. He did not eat a moldy orange on vacation. There were no oranges in this story, although there is something called mold juice. I'm sure you remember from my intro.
Right. I'm not expecting to be a fan of mold juice.
Mold juice
doesn't sound like something I'm going to enjoy.
Well, let's learn all about it in 1928.
So this seems to be not America.
Hello, Governor.
Oh, boy.
Blimey. Cranky.
Yeah. So I take it we're in England right now.
We are... Excuse me, I had a frog in my throat. That's so odd. It made me sound exactly like an English guy.
Oh, yeah.
So
it did.
This story does take place in England. It revolves around Fleming's vacation. Okay, so you did get that part right. He was professor of bacteriology at St. Mary's Hospital in London. In his lab, he left some petri dishes out when he was away on a summer holiday at his country house in Barton Mills, England. He called this house the Dune.
The Dune. Spice must flow.
It sat on a large parcel of land with a meandering river and even a small island. Fleming spent his time relaxing and fishing for pike.
Okay, and this is very idyllic, and I have to say I appreciate that we're in a nice idyllic place for once, but what...
There is a lake here. We could take a boat out?
I'm all set on boats, but thank you for the offer.
All set as in you would love to get on the boat?
I am going to stay right here on dry land.
Fair enough.
But I have to ask, what does this have to do with anything we were just talking about? What bacteria, antibacterial resistance,
I'll get to the point.
What's going on? Okay.
I mean, I only go into so much detail about his vacation because, hey, this might be the most important vacation in human history.
Wow, okay. I'm interested. I'm back on board. How is this the most important vacation in human history?
He began sorting through petri dishes containing colonies of Staphylococcus, a bacteria that causes boils, sore throats, and abscesses. Ugh.
Oh, yeah. I am not a fan of that one.
He noticed something unusual on one dish. It was dotted with colonies like all the rest, except for one spot where a blob of mold was growing. Not bacteria. It was later identified as a strain of Penicillium chrysogenum. This mold produced something that was curiously adept at fighting bacteria. At the time, Fleming called this stuff mold juice. Most people nowadays would call it penicillin.
Okay, so it wasn't a moldy orange, but I had the right idea. He discovered it by accident.
Yeah.
Mold produces something that kills bacteria, right? That's the gist of it.
And to be clear, while Fleming discovered this particular bacteria-killing mold juice, he wasn't actually the first human to realize that mold could be used to fight infections. Thousands of years before Fleming was around, Egyptians, Gina, I will offer this courtesy. I know that you are a germaphobe.
Yeah.
You might want to cover your ears for this next part.
Oh, God. Let's just get it over with.
Okay.
What did they discover?
Ancient Egyptians used to place wadded up pieces of moldy bread on infected wounds to fight off bacteria.
Oh my God. I think I'm going to throw up, David.
Okay, well, not in the lake. The pike are in there.
I think it's over. All right, so Fleming figures out that it is the penicillin or mold juice from the mold that kills bacteria rather than just like moldy bread in general. So we start using this to treat infections right away, right?
Believe it or not, one of the main applications he originally mentioned for this stuff was actually just to keep bacteria from growing in lab experiments.
Wow, that is so funny. It's
Yeah.
like using an iPhone as like a
A
paperweight.
coaster, yeah.
Yeah.
He really was focused on the one thing.
Wow.
Yeah, just keeping bacteria out of his experiments.
Okay, so how long did it take for people to start using penicillin as medicine?
Like about 10 years.
10 years?
10
Are you serious?
years. Yeah. It wasn't until 1939 that a team of scientists at Oxford started researching penicillin and working to turn it into a usable drug. In 1941, a policeman named Albert Alexander became the first recipient of penicillin. He had scratched the side of his mouth while pruning roses and developed a life-threatening infection. It was treated with penicillin, and within days, he recovered. A medical miracle at the time.
Wow, okay, so we're using penicillin. We are saving a life. That's so cool.
Yeah, don't get too far ahead of yourself. Not saving a life just yet.
Why are you
I
making
would
that
say.
face? What happens? What happens to the policeman?
Penicillin wasn't super easy to make at the time, so they ran out of it, and
They ran out?
Mr. Alexander did later die from the infection.
Oh, come on, David.
Yeah.
This is...
But okay, hear me out here. They did figure out, of course, later on how to make the drug more effectively, and it was made available during World War II. I mean, you can imagine it must have saved thousands of lives.
Okay, that is very nice to hear. A little positive turn at the end there.
Yeah.
And, you know, in general, I'm very pro life-saving medicines. I love a story about a life-saving medicine. But David, how does this lead us to antibiotic resistance?
Well, even as he discovered penicillin, Fleming predicted a potential consequence. He wrote, quote, "There may be a danger, though, in underdosage. It is not difficult to make microbes resistant to penicillin in the laboratory by exposing them to concentrations not sufficient to kill them. And the same thing has occasionally happened in the body."
So Fleming was warning that if we don't take enough antibiotics when we have an infection, we may allow the bacteria that survive to develop the ability to resist antibiotics.
Right. And I suppose that's probably why you're supposed to finish your course of antibiotics, right? Even if you feel better?
Well, yes, and for the record, I always do that. But there's actually some debate over this concept.
Okay.
Some scientists suggest that taking antibiotics longer than needed is what we should be more concerned about.
Okay. Why?
Well, remember how we said before that not all bacteria are bad?
Right.
There are harmless species of bacteria in our bodies. Because of natural selection, the longer we expose them to antibiotics, the more resistant they become.
Okay, I thought that you said they were harmless in the body.
Right, they usually are, but they can be what's called opportunistic pathogens. That means if the immune system is compromised, they can become harmful. So we don't want to expose them to antibiotics any longer than we need to.
Okay, so the science is still kind of evolving on figuring out the right duration for antibiotics, I suppose.
Yes, and by the way, always listen to your doctor. Don't go rogue and shorten or lengthen your course of antibiotics on your own.
Right, and as we've said several times at this point, and on my part, reluctantly, we are not doctors, Gina and I.
We are so far from doctors.
Yeah, some further than others. I think I'm pretty close, but...
You might be the furthest.
Okay, let me get this straight.
Sure.
We started making medicines to kill bacteria that make us sick.
Yes.
And in doing that, we created some sort of natural selection pressure that encourages the growth of medicine-resistant bacteria. Do I have everything straight here?
Well, there's something I want to be clear about here. Yes, humans are speeding up the evolution of resistant bacteria and other microbes like viruses and fungi, but we did not create antibiotic resistance.
Right.
This did not all start with us.
Believe it or not, I actually knew that.
Wait, did you say you knew that?
Yeah, I did. In fact, well, I'll just cut to the chase. It's our next inflection point. Gina, thoughts on visiting the Ice Age?
Oh, jeez, David, with these extreme environments. Okay, look, my jacket is in the next room. Give me 1 second. I'm just gonna go grab it.
We don't have time for all this junk. Let's just
Oh,
go
dude,
back
please.
30,000 years ago. Here we are.
David, I am so cold.
You know what? I don't know why. I felt like there was a rush to get out here. I'm freezing. My took us off as well. This is ridiculous.
Yeah, I'm very eager to see why this is necessary for us to be here.
Okay. Well, honestly, this whole inflection point was a surprise to me in all my ignorance. I had assumed that antibiotic resistance would come after antibiotics, the drugs.
Sure. I mean, I can totally see how someone might think that. I mean, I obviously knew that that wasn't true, but,
Well, a little over a decade ago, scientists analyzed DNA that had been frozen in time, literally frozen, in ice for 30,000 years.
That's this ice, I assume, that we're standing on?
That's this ice. We're standing on this ice.
Okay,
and
got it.
in that ancient DNA, they found genes that encode resistance to tetracycline, beta-lactam, and glycopeptide antibiotics.
Those are all really common types of antibiotics that we use today.
Right.
You're saying they found resistance to those in DNA that existed 30,000 years ago?
In this very ice, yes.
Wow.
Pretty wild, right? I mean,
That's
before
pretty wild.
we were even close to discovering these types of antibiotics, bacteria had already had the tools to be resistant to them. And we can actually go even further back than 30,000 years. Bacteria was actually discovered in a cave in New Mexico that scientists believe had been isolated for 4 million years.
Whoa.
Some strains that were found were actually resistant to 14 different commercially available antibiotics.
Wow, okay. And by the way, I'm grateful that you didn't make us go back 4 million years.
Although New Mexico sounds a lot warmer than here.
Well, 4 million years ago, I don't even know
It's-
what it was
It's
like.
anyone's guess.
Anyway, I still don't really understand why bacteria would produce antibiotics in the first place. Is it that they used antibiotics to kill other competing bacteria?
That's one possible explanation, but there are other theories. There's some evidence to suggest that bacteria produce antibiotics as a way of communicating with other bacteria.
Seems like a dangerous way to communicate.
It is kind of odd, but they can release the antibiotics in concentrations low enough not to kill other bacteria, and they can actually serve as signaling molecules. Pretty cool.
Yeah, okay, but what about resistance?
Okay, so it sort of makes sense that if bacteria are going to produce antibiotics, they would have the ability to resist those antibiotics. So they don't get poisoned by their own stuff.
Sure, okay.
It also follows that they would develop resistance to antibiotics produced by competing bacteria. Plus, they can pass down resistance from one generation to the next.
Actually, what's really wild is that bacteria don't necessarily have to inherit resistance genes from their parents. They can also get genes from other bacteria in the microbial community.
Okay, so one sprinkle-shaped bacteria.
They do not have to be shaped like a sprinkle, but yes.
Okay, well, this non-sprinkle bacteria could make a copy of some of its genetic material and just give it to another bacteria?
Yes. Isn't that wild?
That's insane. We couldn't do that, right?
No, David, humans cannot do that.
Okay, well, don't act like that's such a silly question. I'm sure you would probably want a copy of my inflection point finding gene.
I already have like a being really smart gene, so I don't know if I have room in there.
Fair enough. Yeah, okay.
You get it.
Hey, just between you and me, can I have some of the really smart gene?
Let me, I mean,
Oh, okay.
I can check.
Well, if you don't have a
I
lot
don't-
to spare, I guess that's what it sounds like. But back to antibiotic resistance. I get that it's basically ancient, but let me get this straight. Since we've started using antibiotics as medicine about 100 years ago, we've actually just been making this whole thing worse?
That's right, yes.
Okay, well, that sounds pretty bad.
It's not great.
So I have another question, and I think this one is not silly, right? Okay, if antibiotic resistance keeps going the way it's going, how bad can things get? What's the worst case scenario?
David, I actually hate breaking bad news to people.
Okay.
I don't know if you knew that about me. It's such a bummer.
So you're not going to answer my question. You're not going to tell me because it's bad news?
Well, I'm not personally going to break the bad news. I am going to ask somebody else if they will do it.
Sure.
Rowan, you are up.
Hey guys, thanks for having me on. I'm Rowan Walrath, and I'm an associate editor and life sciences reporter at Chemical and Engineering News.
Rowan covers the biotech and pharma industry, and she's particularly interested in the forces that motivate which drugs get made.
And antibiotics are a very, very essential part of that.
So, Rowan, help us out here. Let's say we get to a point where basically no antibiotics are effective against bacteria anymore. What would the world look like at that point?
So let's say I am out gardening and I am trying to prune my incredibly overactive rose bush, and I get a thorn snagged on my finger, and it's a pretty bad cut. It's not feeling good. Over the next couple of days, it's just getting increasingly worse. It is getting yellow, there's red around it, there's like gunk in there that's really not looking so good. And then the redness begins to spread down my finger.
Okay, wow, that sounds painful and
Yeah.
eerily familiar. You know, the whole rosebush thorn thing
Yeah.
reminds me of that guy from earlier. But,
Right.
you know, they didn't have Neosporin back in the day. Nowadays, couldn't you just put some Neosporin on your cut and call it a day?
Well, Neosporin is an antibiotic ointment.
Oh.
So in this theoretical scenario, Neosporin doesn't work against bacteria anymore.
Okay, well, there's got to be some other way to fix it, right?
So I have a couple of options because I don't have antibiotics available to me. I can have my finger amputated, which is also maybe not a great scenario if you're not able to effectively cauterize the wound, which is an open question. Or I can wait and hope for the best, and in a worst case scenario, the infection could enter my bloodstream and kill me. That is the stakes that we would be looking at, and it will probably take a while in this doomsday scenario for that to actually unfold, but that is sort of the nightmare if you take it all the way to its potential result.
Okay, man. I mean, I have rose bushes in my backyard, and I'm sure if I ever got around to trimming them, I might get cut really easily.
Well, you know, again, we are not in this scenario yet. This is all just hypothetical. So you'd probably be fine
Okay.
if you cut yourself on a thorn today.
Whew, phew.
But while we might not be in the doomsday scenario right now, antibiotic resistance is still a serious global health threat. A study in The Lancet estimates that in 2019, bacterial antimicrobial resistance was responsible for more than 1 million deaths. And while it affects every country around the world, the places that are most affected by it are low and middle income countries.
So, what are we doing to try and stop this, or at least slow it down?
Well, we discussed before the debate about taking too few or too many antibiotics. One thing that scientists do seem to agree on is that prescribing an antibiotic for an infection that a patient doesn't have can contribute to resistance, and we should try to avoid it whenever we can.
Okay, hold on a second. Why would a doctor prescribe antibiotics for an infection a patient doesn't have?
Well, one reason this can happen is when a patient is very sick. Sometimes a doctor doesn't have time to wait for diagnostics, so they treat with a broad spectrum of antibiotics until they can figure out what's causing the illness.
Okay, so it's a diagnostics issue?
In part, yes. The faster we can diagnose people, the sooner we can figure out which antibiotics will help them. That way, we wouldn't have to throw the whole kitchen sink at them.
Okay. Well, I actually know of one diagnostic tool that has already helped with this quite a lot.
You have this, I'm about to do an inflection point look on your face.
That's not true. I look like this all the time. Maybe I'm always thinking of inflection points.
Okay, then.
So I guess we have to start the story at a certain time. It happens to start quite a bit of time ago. I guess you could say like, oh, you know, let's go back to 1969 or something.
Sorry, did you say let's go back to 1969? Because that sounds very inflection pointy
Okay,
to
fine.
me.
All right, you got me dead to rights. We're gonna do an inflection point, okay?
I knew it.
The ruse is over.
Okay.
I give up. Let's go back to 1969. Okay, Gina, since we've established that you are very smart,
Correct, yeah.
what is so special about 1969?
Let's see. It was a jam-packed year, a groovy year.
Very groovy.
There was Woodstock. There was the moon landing.
Yep.
And what else? Scientists discovered the bacteria Thermus aquaticus, which eventually led to the
What are you doing?
invention of polymerase
You're reading
chain
my notes.
reaction,
You're literally
or
reading.
PCR.
You
You gotta stop leaving them out like
you-
that. You're
Okay.
just setting yourself up.
Yeah, blame me for you cheating. I'm looking on my note. I mean, this is ridiculous.
That's fair. Okay, I was looking
Now
at
that now that they are out, I'm tucking them under the table here. What is Thermus aquaticus? Can you tell me that?
Okay, I mean, I can guess. Thermus aquaticus, so
Yeah,
heat,
Thermus aquaticus.
water. It's like a bug or something that likes heat and water, I guess.
Maybe you are a
Is that
genius
close?
after all.
Well,
It's a bacteria that can withstand really, really hot environments and even, boiling water. It was first discovered in a sample of water that was taken from Yellowstone National Park.
oh, okay, where the geysers and the geothermal vents are?
Yeah, exactly. Doesn't seem very hospitable to life.
Sure.
So scientists took sample after sample of this water from Yellowstone back to their lab and kept that water at boiling temperatures for days. After watching these different samples, they noticed in one sample that there was something in there swimming around, even reproducing.
Okay, whoa, that is really surprising. But when I was reading your notes earlier, it seemed like
Okay.
this had something to do with a test called polymerase chain reaction, or
Right.
PCR. What does it have to do with that? How does it connect?
Right, okay, so the PCR test, which, as you said, stands for polymerase chain reaction, is a test that can be used to diagnose illness. This test can do a really great job of narrowing down what type of infection someone might have.
Right. The test works by making millions of copies of a small piece of DNA so it can be detected more quickly. Instead of hunting for a small piece of DNA, we're copying it millions of times, so it's a little more easy to identify.
Exactly. In fact, the key person in inventing PCR, Carrie Mullis, said that trying to isolate a piece of DNA was like trying to use a telescope located on the moon to read license plates down on Earth whizzing by on a dark highway.
Okay, kind of a convoluted analogy, but I think I get it.
To continue this analogy, everyone at the time in science was basically trying to make a bigger and better telescope. Carrie's idea was, what if instead we just made the license plates themselves much easier to see from the moon with that telescope?
Okay.
What if instead we copied one license plate so many times that it covered, say, all of North America?
I think I get the principle of this. This would make it easier to glean information from the license plate if it were copied millions of times. But in this analogy, like the letters on the license plate would still be small. There's just a lot of them.
There's just a lot of them. Yeah, I mean, maybe we've stretched the metaphor to its limit here. Just know that
Okay.
in the microscopic DNA world, this makes sense to make all these copies.
Okay, got you. Bunch of copies, helpful. I will take your word for it.
So in order to make these copies, you have to heat up DNA. You have to split it apart right down the middle. Zipping
The
it.
DNA, the double helix,
Yeah,
we're just going to cut it right down the middle like a zipper.
just like a zipper. Then a special enzyme, Taq polymerase, remember that enzyme,
Okay.
is used to build two new strands of DNA from the two split halves. Now you have two copies of that original DNA. And Gina, guess what?
What?
You can just keep doing that again and again and again. You can repeat that process indefinitely.
Okay.
The next time you get 4 copies, then 8, then 16, 32, carry the 4, let's see, just one, then 64, and then after
64,
that, let's just say you're off to the races.
Okay, got it. So this enzyme just helps continue doubling and doubling and doubling
Right.
the DNA. And that's good because then you have all the copies you need.
Exactly. All right, great. Wow, another episode in the books.
Well,
We should get our post-episode pizza, right? I put that order in right now.
You still haven't explained Thermus aquaticus, the thing you mentioned in the beginning.
Right. Sure. Well, it's actually pretty simple. The Taq enzyme that I mentioned, the one that helps duplicate this DNA so we can do this whole chain reaction thing, comes from Thermus aquaticus. Scientists needed an enzyme that could withstand the extreme temperatures that happen when they're splitting apart the DNA. Without that bacteria that we discovered in 1969, PCR testing might not have happened. We needed that special enzyme.
So back to antibiotic resistance, it sounds like PCR testing can help identify and diagnose infections. In fact,
Right.
I remember PCR testing came up a lot during COVID, especially in the early days.
Yeah, basically as soon as scientists published COVID's genetic sequence, labs could design PCR tests for it. PCR is also really sensitive. it can find even a few copies of viral RNA in a sample. Okay, so we've got faster, more accurate diagnostics than we used to have, but surely there are some other ways to stay on top of this problem, right?
Well, it's not a perfect solution, but one thing we can do is continue to come up with new antibiotics.
Oh, okay.
Basically, after we started using penicillin, we've sort of been in this cycle where we keep coming up with some new antibiotics, resistance develops to those, we come up with some more,
Sure.
and so on and so on.
Got it.
But even that is not quite as simple as it sounds, at least not anymore.
Oh, no. Okay.
Yeah.
Why can't we just keep churning out new antibiotics?
It turns out the answer to that is pretty complicated. Let's bring Rowan back in.
So basically, researchers find new antimicrobials through wholesale screens of soil samples and things like that. But scientists eventually hit diminishing returns. So in the 1970s, these wholesale screens kind of just started turning up compounds that researchers had already discovered, and the rate at which they were finding new antibiotics really dropped.
So, antibiotics are even harder to find now. I imagine that doesn't necessarily incentivize people to go out and try and discover new ones.
Yeah, and that's not the only disincentive. As we started to talk about before, one way doctors try to combat resistance is to avoid overusing antibiotics. Keeping antibiotic use limited is, well, not a compelling sell for people who would earn money from developing and selling antibiotics.
Right.
If I'm an investor and I'm considering funding development of a new antibiotic, you've just told me that doctors aren't even really supposed to use that antibiotic except in relatively limited circumstances. So that means there's next to no return on investment for me, and the threat of resistance is still there, right? So best case scenario, I'm making a couple $1 million. It's certainly not the multi-billion return that you could get from other types of drugs. And this has killed a lot of companies that were otherwise developing promising new antimicrobials.
Boy, there's got to be some way we can incentivize people to start making antibiotics again. Maybe you and I can brainstorm right now.
Oh, okay, sure.
With the world's smartest woman.
Yeah, close anyway.
What if we give everybody at these drug companies free coffee for a year?
Okay.
I'm not talking about the big crafts at like conferences or whatever. I'm talking about really good coffee, like pour over, single origin,
small batch.
I think this is a winner.
Sounds like a pretty good idea to me.
Yeah.
But believe it or not, smarter people than us are working on ideas for how to incentivize antibiotics. And these incentives
Smarter than us.
typically fall into two categories: push incentives and pull incentives.
So this upfront investment, I give you money, you go and make something, that's what's called a push incentive. So the people who are concerned about antibiotic resistance growing, they also advocate for what's called pull incentives. That money exists sort of on the other side of the approval stage, to oversimplify a little bit. One big example is the Pasteur Act. You can think of it like Netflix for antibiotics. The government pays for access and providers use what they need. So the plan would ensure that drug makers get paid for new antibiotics regardless of how much they actually sell.
Wow, that's an amazing idea. I hate to admit it, but that's even better than like really nice coffee.
Maybe just a little.
So what, we've totally solved the antibiotics incentives problem?
Well, not exactly.
The big catch here is that the Pasteur Act has been introduced 3 times since 2020. It has never made it out of committee. So it's just not feasible for drug makers to wait around for its passage.
I should have known. I should have known, Gina. I should have known not to get my hopes up.
Yeah.
Yeah,
but...
What are we doing?
But hey, the Pasteur Act isn't dead. A subscription model like this could still, one day, be implemented. Or we could come up with another creative way to incentivize people to find and develop antibiotics.
Or I could prick my finger on a rose bush and end up having to chop my arm off.
Well, I don't think you need to be worried about that quite yet.
I just hope it's my left arm. I would hate to lose my podcasting arm.
Oh boy, what is your podcasting arm?
I'm sure you've noticed. I with my right arm, I hold my mic in like a cool way. Like, kind of makes me look like a cool podcasting guy.
Sure.
Yeah. Check it out. Here, I'll show you.
Okay. Oh, yeah, that. Right. That looked really cool.
I think I pulled a muscle.
Probably.
I might have to
dare to
switch over to
say-
the left arm soon anyway.
I
Jesus.
think you could probably like knock your mic over with either arm.
Well, it just wouldn't be the same.
Yeah. Well, maybe we can cross that bridge when we get there. But for now, at least we understand antibiotic resistance a little bit better. Thanks, Rowan.
Thanks for having me on.
Man, antibiotic resistance is kind of spooky.
Hey, why don't you tell me about the next episode's inflection points? That always cheers you up.
I guess. I mean, I don't really know if I'm up for it, to be honest.
Oh, come on. Tell me about how in 1792, a Greek scientist
Okay.
put a lizard on his doorknob,
Not sure what
and
we're
now
doing
we have
here.
cell phones.
Put a lizard on his doorknob? That's...
I don't know.
My-
I'm just making up an example.
My inflection points don't sound like that at all.
Okay,
I
they
don't know where you
literally
get stuff like that.
sound exactly like that.
All right, I will prove it to you right now. I'll just
Sure.
read off the next inflection points. You'll
I'd love that.
listen to them and you'll go, oh my gosh, I don't know what I was talking about with this 1792 Greek scientist put a lizard on a doorknob and now we have cell phones. That's
Great.
I don't know where you get this stuff.
Happy to be proven wrong.
So the first one is, in 1791, there was an Italian scientist hanging frog legs from his fence during a lightning storm, and he discovered what he called animal electricity. And then, in 1859, a French scientist invented a device that, with a few alterations and improvements over the many years, is still being used in cars today.
Cars today, okay.
And in 1973, there was an oil embargo. And I mean, that's as far as I can say about that.
Okay, so 1791,
Yeah.
hanging frog legs from his fence.
Yep.
Sounds a little bit
Yeah.
close to what I said. I don't.
Well, I don't.
Okay,
I don't
1792, I think I said.
1792. Yeah, it's a totally
somebody
different
put
year.
a lizard on their doorknob. I mean, that's come
Lizard
on.
is different
like
than frog, so
a frog and a lizard. I mean, is
And
it
the cell
though?
phones
Is
thing.
it that different?
what is that? That
And
doesn't
oh
make any
right,
sense.
and now we have cell phones. Oh, you're right. So I'm sure that the next episode topic has nothing to do with cell phones, right?
Shoot. You know, I actually have
Check your
I have
notes there.
I have something that I have to go to. There's like some other
Oh, you've got a
different
thing?
that
Yeah.
I think I should just
You're just gonna go.
yeah. I don't need to answer about the cell phones and stuff like that. That's we'll figure that out in the next episode.
That sounds good. Inflection Point is a podcast project from Chemical and Engineering News.
Chemical and Engineering News is the official news outlet of the American Chemical Society.
Music by Kirk Onstad and Shutterstock.
Written, produced, and hosted by Gina Vitale and David Anderson.
Additional audio production by Jeremy Barr.
Thanks for listening.